Hi, I'm David McNamara, a lecturer and structural geologist from the University of Liverpool.
I'm Jen Roberts, Chancellor's Fellow in Energy at the University of Strathclyde in Glasgow.
And I'm Chris Yeomans, a Research Fellow at the Camborne School of Mines, University of Exeter, down in Cornwall.
So welcome from all of us to TSG at 50 celebration session on structural geology and net zero. In this short presentation, we want to reflect back on TSG's track record over the past 50 years, connect the past to the present and future of net zero aligned research, and give a future look. Underpinning the delivery of a low carbon energy future is the sustainable and innovative use of our subsurface resources, whether that's going to be for heat, energy, or materials. And tectonics and structural geology is crucial to that. We've seen shifts and changes in structural geology research over the previous decades, and all of them in some way can and have mapped into and onto net zero applications. We absolutely need to continue to support skills development in this space and continue and enhance our encouragement for the uptake of earth science in society and education. While our gloriously nerdy, rocky research and its application is important, so too is our advocacy for structural geology and geoscience more broadly, and our ability to translate and communicate that research for the range of net zero geoscience applications. We also need to break down barriers to inclusivity in our field so that we can maximize the chance of achieving our global sustainability goals. But before we get into that, Chris is first of all going to tell us what net zero is, where it came from, and what it means.
Thanks, Dave. So the term net zero became mainstream following a 2018 report by the Intergovernmental Panel on Climate Change, the IPCC, which was commissioned as part of the Paris Agreement. Net zero specifically addresses CO2 emissions, countries where total CO2 emissions must equal the amount of CO2 sequestered on a national scale. The report presents three models for the likelihood that by achieving global net zero CO2 emissions, the global temperatures will be limited to a rise of 1.5 degrees centigrade by 2100. However, these models also require a significant reduction in the other greenhouse gases, and these are not considered within a net zero budget, but are critical to the 1.5 degree target. The best case model in blue targets net zero CO2 emissions by 2040. The moderate case is represented in grey above this in the graph and accounts for net zero being achieved by 2055. To be effective, both of these models require a significant reduction in non-CO2 greenhouse gas emissions by 2030. In purple, the worst case scenario models for the effect of not reducing these other emissions, even if net zero is met by 2055. What is notable for all these models is the significant overshoot we see regardless of if we achieve the best case scenario. And the spike that has already been broken through above this 1.5 degree threshold shows how imminent our problem really is. So ultimately, the term net zero does exclusively refer to CO2, but the concept is reliant on the significant reduction of other greenhouse gas emissions to achieve that target of a minimum rise of 1.5 degrees centigrade by the year 2100. The question is, how can we as structural geologists assist the world in this challenge? And Jen is going to start us off.
Thanks, Chris. So let's have a look at the ways that structural geology fits to net zero. We've mapped out the key themes here in this diagram, and we don't claim that this diagram is comprehensive, but we've identified topic areas in green, applications in blue, and then various aspects of tectonics and structural geology, including skills, approaches, and fields in yellow all around, a kind of word soup, as it were. And really, all of these map into resources, whether it's energy, as we'll go into more detail in a moment, whether it's water provision in a changing world, minerals and mining for net zero technologies, or doing so more efficiently and more locally, or making sure that future turbines or wind turbines have stable foundations, or making sure that infrastructure of the future is resilient to natural hazards. And of course, key to all this, and so leading on the right of the image, is communication and knowledge translation, whether that's to support interdisciplinary working, or to inform policy, or to inspire geoscience interests more broadly in society. And on that note, this map really brings to the fore how utterly important structural geology and the related skills and fields are in supporting our sustainable future. The notable downturn in students studying geoscience is deeply worrying, to the point that part of us supporting our net zero future is to support geoscience uptake from the early years and to be earth science advocates ourselves. And through the years, TSG has given us all a supportive and creative environment to talk about cool rocks, techniques, failures and field anecdotes and so on, all of which will have contributed in some way or other to keeping us within the tectonics and structural geology community, within the discipline or the path, stopping us from leaking out the leaky pipeline. And these networks are really valuable for that. I don't want to underestimate that. But reflecting back on 50 years of TSG, what have we been studying and how have things moved or changed? We looked to the abstract booklets to help us. We'd have loved to have sat and flicked through all the abstract booklets that have ever existed, but we're relying on the ones that we could find in our colleague Zoe Shipton's office, in my bookcase and in digital form online. A massive thanks to Chris McMahon for supporting on that. Doing this gave us insight into the talks, topics and special sessions from 4 AGMs in the 2000s and all of the past decade as well. And aware that we had gaps and particularly a positive bias towards the TSGs that we attended and presented at, we asked some of the TSG stalwarts to reflect on this as well. So thanks to those of you who offered their thoughts. And this is what we mapped out. We see that there's been a really clear shift and change in focus and application throughout the decades. First, it's worth that we didn't really talk about application in the early years of TSG, simply the processes and observations. But the applications are mostly around hydrocarbon systems. And the study of coal tended to inform that, given the decline of the UK coal industry from that time onwards. We also see a shift towards more applied research only in recent decades, including what we'd identify clearly as net zero aligned applications, with CO2 storage first creeping in the early 2000s and hydrogen mentioned for the first time by Chris's talk in Hull in early 2020. Geothermal appeared surprisingly late, so perhaps we missed some earlier talks. And the first mention of policy seems to be my talk in Edinburgh in 2015, so perhaps we're missing some of the picture there. So we welcome your thoughts on that. But the TSG community has been studying some awesome rocks and systems from around the world and beyond with a range of tools, and the research at TSG is built and built and built on each other, progressing knowledge, and much of the outcomes that we've come up with are translational. So what we learned about fault seals for hydrocarbons is utterly important for fault seals for CO2 storage, for example. And in that way, or in that sense, the past is the key to the present. And with that, we're going to focus on a couple of case studies of geoscience for net zero, and I'm going to start that by zooming into the role of subsurface for net zero energy. Now, this stuff at the top here in green is often the sorts of visuals that you see when we're talking about a low carbon future. This image itself is from the Scotland's energy strategy. What these images don't show is the stuff beneath our feet, the stuff often depicted by a lovely popular colour, brown. The use of subsurface resources underpins the delivery of this green, futuristic energy future, whether we are putting stuff in the ground for it to stay there, such as for CO2 geological storage or radioactive waste disposal, whether we're taking energy out of the ground, whereby fuels or heat from deep or shallow geothermal resources are extracted and used, or whether we are repeatedly taking stuff into and out of the ground for energy storage, like hydrogen, compressed air or thermal energy. And these examples are not exhaustive. There'll be other novel resources yet to be identified or considered, and we need ingenuity for net zero. But together, geoenergy resources and the technologies that access them offer ways directly or indirectly to deliver clean or cleaner energy as we move towards and live in our net zero world. Remarkable growth in the use of our geoenergy resources is forecast. This offers quite a technical challenge and presents other challenges too, as I touch on in a moment. But critically, all of these applications need to be grounded in structural geology, from the understanding of the resource itself and how to manage it, to understanding uncertainty and de-risking the activities and designing of the monitoring plans. And this improving understanding of leakage pathways and translating this to monitoring approaches is where I've been working for over a decade. My research spans from the very scientific, like studying gas seeps from around the world, quantifying gas emissions, assessing storage security, to the social scientific, understanding physical and cognitive bias and geoscience data collection, shaping geostorage site selection and policy, to the very social, like risk communication. And I've been lucky enough to work at natural analogues for CO2 seepage of all types and scales of emissions. Here in Italy on the left-hand side, in Australia in the middle, and more recently working on hydrogen seats with PhD student Chris McMahon. And I've also been very lucky to be involved in field experiments to simulate leakage. Now, these field experiments are a fantastic way to test and validate our understanding of rock properties and fluid flow. And these photos here of CO2 bubbles at the Quicks offshore CO2 release experiment in 2012, and me at the In Situ Fault Lab in Western Australia, where in early 2019, CSIRO injected CO2 into a fault zone to inform monitoring and verification approaches. How cool. And what a great excuse for missing TSG that year. And of course, now we have other geoenergy observatories closer to home, quite literally for me, with one of the UK GEOS sites just down the road from where I sit here in Glasgow. And that site's to inform on geothermal, with a focus on coal mines for heat. And there's something quite beautiful about coal mine geothermal, where our coal-laden past might now provide resource to unlock low-carbon heat systems of the future. Again, the past is the key to the present, and this also fits with the circling back towards local energy provision, having once moved towards a centralised energy system. I'm using coal mine geothermal here as an example, where there are absolutely hordes of gorgeous structural geology to be done. Just check out some of Billy Andrews' recent work on that. But whilst we're doing that, it's really important to be aware that ex-coal mining communities are proportionally more deprived and thus proportionally with greater fuel poverty than elsewhere in the UK. So factors of politics and heritage are at play. And in my view, recognising that our science isn't removed from society is really important. Such social scientific or social geological challenges are particularly prevalent for topics that are unfamiliar, uncertain or emerging, and where change is needed fast. Topics like the subsurface, like these new energy resources that I've listed before. The many applications that geoscience underpins for net zero are deeply embedded in issues of social and environmental justice, and we can't and shouldn't disentangle from our work on that. So with that, I'm going to hand over to Chris, who's going to take us from these field sites and over to the southwest of England.
Thanks, Jen. There are significant advances to be made in the way we structure our economy, not only in the manufacturing of products, but the responsible sourcing of materials. The circular economy looks to make efficiencies within the way we operate and takes a life cycle approach to modelling the reasons for sourcing materials from a certain region, or even citing new industries in a particular area. In the example I present here, which is largely based on a concept from southwest England, we could build a deep geothermal power plant, which could include electricity generation as well as heat, much like the active project at United Downs that is ongoing at the moment. And this sustainable energy source could be used to reduce the carbon emissions of a mine that is extracting vital metals to keep building the smart products we all use and eventually replace every couple of years. On top of this, direct metal recovery from these geothermal fluids may also be possible and expands the list of different metals available for extraction. Thereby, we can create a responsibly sourced metal supply for high technology products such as smart devices and possibly electric vehicles, whilst offsetting the potential CO2 emissions. Those in turn offset other non-CO2 greenhouse gases as we move towards a cleaner energy consumption, especially from the transport industry. However, for this to be achieved, we still need structural geologists. We need them for fracture mapping, for geomechanics, reservoir modelling and optimisation, for play analysis, stealing the prospectivity modelling from the petroleum industry and applying it to geothermal energy. We also need structural geologists for mineral deposit modelling, resource estimation, 3D mine design and geotechnics, all to get those important metals out of the ground. I'll now pass back to Dave for a look at the translational future of structural geology.
Thanks, Chris. One thing I have learned in my career is that a structural geologist is adaptable. I discovered this personally when I entered a geothermal energy consultancy role as a structural geologist, coming out of a PhD that looked at the microstructures and fabrics of aqueducts in the Italian Alps. Working on geothermal systems in countries where they have utilized this energy resource for a long time really opened my eyes to the various roles structural geologists play in reservoir geology and resource management. Now, with more interest in geothermal electricity and geothermal heating growing here at home, with great examples in Glasgow, Cornwall, and more, I see new spaces for our strong structural geological community to apply their skills and contribute to geothermal's ability to assist with net zero in the UK, as it does successfully elsewhere in the world. With deadlines set for net zero and a focus on energy transition and decarbonisation, it is really important to recognise that we as a structural geology community already play a significant role in this space, and we have room to expand that role quite dramatically. Structural geologists have been an important part of the geoscience side of energy for decades, given their role not only in fossil fuels, but also in geothermal, nuclear power, and anywhere ground stability studies are needed for things like hydrodams or windmill farms, for example. That role remains in our future, but the focus is shifting from where we have commonly applied our skills and talents as we gear up to tackle the geological needs of a changing energy industry landscape. As we gradually move away from fossil fuel energy dependencies, the skills honed there remain important as they are highly translatable to other subsurface resources that we need for a greener energy sector, such as geothermal reservoir characterization, operation and monitoring, or characterization and microstructural investigation of vein ore bodies with energy critical elements for green tech manufacturing. Though the market is changing for us in the way we have traditionally engaged with it, there is a new and growing market that requires us. We don't need to reinvent the wheel to have a future in energy. And we have never had a better and more diverse toolkit to contribute, with our field geology and mapping to new remote sensing techniques for mapping faults, developing new tools to capture structural information from wells, working with geophysicists to interpret structure from seismics, magnetotellurics, and other techniques, and huge steps forward in computing, allowing us to model 3D structure, fracture network models, and geomechanical modeling. With all of this ability, we have a guaranteed future in a net zero sense, and there is plenty of room to keep developing our fundamental structural geology research to contribute to this space as well. TSG has always been a place where structural geologists have shared their research from all parts of the globe and even off planet. With the global issue that is net zero and climate change, our role in resources and the processes that impact them does not change. When we look at maps of where decarbonizing geological systems and resources are located, we can easily see that our international work can continue with a global future context. This future will also include continued work in international fossil fuels. A transition away from fossil fuels means more than removing our need for it as an energy supply resource, but also relies on the work others are doing in the wider scientific community to innovate replacements for fossil fuel products that are intricately tied to many green energy materials, whether that's coal that we use to make steel for windmills or petroleum for plastics that are used in electric cars and solar panels. There will be an ongoing need for fossil fuel products during an energy and materials transition, and that needs good geoscience to help do it more safely and more environmentally than ever before. Finally, two heads are better than one, and more studies are now showing us that when different types of heads from all types of backgrounds get together, insights are deeper, skills are integrated, and great science can be achieved. We have to make sure our TSG community continues to work harder at making this easy to do, that we create and foster an environment here and internationally that welcomes talent from all areas and works hard to remove barriers to diverse voices in our community. And diversity goes beyond the aspects captured on the screen here. It extends to other things like career stage, interdisciplinary interaction, academic industry crossover, and much more. A diverse structural geology community mixing ideas and openly sharing information will be absolutely crucial to delivering the geoscience contribution needed to deliver net zero by 2050. Thank you for listening to our presentation. We've shown that TSG over the decades has contributed in incredibly important and useful ways to areas like energy and resources, which are a critical aspect of the concept of net zero. And hopefully we have also conveyed how TSG will continue to play a really important role in the future. Thank you.